So yeah, I'm probably not going to, I have 90 minutes.
Yes.
And I will probably not use all 90 minutes. I took a 50-minute talk and added a bit extra to it. So it might be 60 plus change. And then if you really are enthralled, I can ramble for some more time after that, if you'd like. So everything is joint work with Gianluca Basso. Here, so everything is joint work with Gianluca Basso. And our setting today is in the world of definable topological dynamics. So let me just warn as a warning. Right. So there is quite a bit of model theory background to get through. But the good news is that at the end of the day, it doesn't really matter. So I will present that background because I have time. But if you at any point get like lost in the weeds of like model theory definitions, the good news is that at some point it'll stop mattering and it'll become more of a set theory talk. Right. So we're talking about the dynamics of definable groups. So these are groups definable in some structure, meaning you have a formula, possibly with some parameters, actually like defining membership in your group, and then you have another formula, again with possibly some parameters, defining the multiplication map. So some prototypical examples that I'll sort of run with. We have the circle group. So take our model here is going to be the real closed field R. And then among pairs of R, I can pick out those pairs x, y satisfying x squared plus y squared equals 1. I get the circle, and then you can define addition similarly. Another example, same structure, real closed field R. We can look at matrices with determinant 1 under multiplication, and that's a nice group. And again, I can carve out that set of 4 tuples and the multiplication using formulas in the language of fields. And so what is kind of fun about the whole enterprise of definable groups, definable dynamics, is this idea that I can plug in other models here and get other groups and then ask, okay, I have groups obtained using like elementarily equivalent structures. Can I say anything about how the dynamics might be similar or different? We'll touch on that a little bit.
So the bigger structure is always a group. I mean, otherwise we just take some fragment of set theory.
No, the bigger structure doesn't have to be a group. And yes, you can do this. Like, so you can take a like just a group, and yeah, so a group is definable in itself, of course. If you want to add a whole bunch of predicates to define every single subset of your group, you can do that. It's very flexible.
Talk about flexibility. Let me ask the questions, and it's perfectly all right if you say that. We'll get to that later. So you're talking about first order. What's crucial about first order? Is it compactness?
Compactness, just the tools from model theory that we know and love. In particular, I might say, I'll say like one word, like exactly one word later about this mysterious object G00. And so you need to know things about like types and like boundedness and your monster model.
Sure, all that stuff. But for example, since you're talking about dynamics, I think, continuous functions and all that. So I asked, what about continuous?
Oh, very, very much so. That's actually something I'm kind of interested in, is trying to push some of this to groups definable in continuous logic. It would work.
Okay, good.
It should work pretty analogously. All right, and so for a bit of abstract discussion, we're going to be talking about like groups just equipped with some Boolean algebras. And let me just mention at the outset, whenever we have such a definable group, we get 2 Boolean algebras on it. We're mainly going to consider the second one, but I'll tell you about both of these. So first, Boolean algebra, just definable subsets with parameters from the structure M here. The second one, same idea, but now the parameters are going to be allowed to range from outer space. So formally, stick M inside some really, really saturated M plus monster model, if you're comfortable thinking about that. And then it's just definable subsets of G, but now the parameters come from this monster, so externally definable. And I'll just mention about these Boolean algebras. These are two-sided invariant under the group multiplication. They both contain all finite sets. For these examples, they coincide, but that's not true in general. And we're mostly interested in that second one. Yeah.
About this. Externally seems to, the way you described it, externally seems to belong in both of these. It's just how external.
Yeah. So yeah, we always need parameters. Yeah, we should always allow parameters.
Right, and but in the first one, you're defining subsets of the group inside your
Inside M.
first
Yeah.
order
Yeah,
structure.
using
So
parameters
elsewhere,
from
R
M.
before,
Yeah,
whatever.
exactly. And then R just happens to be a very nice model of RCF, and so that's why it coincides. All right, so for a second, let's just kind of work at this level of abstraction. So I have a group equipped with a two-sided invariant Boolean algebra containing the finite sets, and so I'm just going to call this a definable group for the moment. And this gives us a compactification of our group. I can form the stone space of that Boolean algebra, and we get some nice compact Hausdorff space.
Can you repeat this? What the two-sided invariant?
Oh, just, I mean, I have a subset, and I can translate it by multiplying on the left or by multiplying on the right, and I just want both of those translates to be in as well.
You said compactification here. That's not just compact, it's needs dense subset of the
Yes.
compact.
Yes, and embeds into, and because our Boolean algebra contains all finite subsets, that will help to ensure that this
Oh, so
happens.
it's telling me what I didn't know. Boolean algebra has all finite subsets, then.
So not only dense, but dense open. All the members of G will be isolated.
So the stone space actually turns out to be a compactification, which in general, it's not the case with stone space.
Right.
All right.
All right, and so now, given a group with this structure, we're thinking topological dynamics. So this is the setting of these G flows. So our group is going to act by homeomorphisms on a compact Hausdorff space X. And we're going to really be thinking about minimal flows. So just when every orbit is dense or equivalently no proper subflows. But now which G flows behave nice with respect to this Boolean algebra? Let's define it to be these G flows. So I look at a point in my G flow and it moves around under the group action. This gives me a map from my group to the compact space X. And I ask that this always continuously extends to this compactification. And then in the case where we actually have a definable group in a model, I'll call a G flow either definable or externally definable to indicate which Boolean algebra is being referred to. Again, most of the time, external definability is the nice one. They're both spaces of types. So I think for definable, that is clearest because it's just ultrafilters of definable sets. So it's like literally a type of n tuples over M. The SGXed M, those are global types. So types over your monster model, which are finitely satisfiable in G. So both can be viewed as type spaces. So a bit of history. This was much of this was pioneered by Newelski in this JSL paper 17 here. And he observed additionally that if we add some more restrictions to this setup, we will get a huge payoff. Like we want to develop topological dynamics for these definable groups. And to do that, we need this property. So this name, as far as I can tell, isn't standard. I just needed a placeholder name. So let's call this thing strongly definable. So I take this compactification, stone B. The group acts on it just by translating the sets. So we have a very nice, it is a G flow. Is it definable in the sense that we defined earlier? So that's a question. It's not always true. Sometimes it is. And in the case it is, it's really nice. So we'll call such B strongly definable groups. And then you can develop a lot of topological dynamics. So if stone B itself is definable, it is going to be the universal B definable ambit. Ambit here just meaning flow with a distinguished dense orbit. We can equip stone B with the structure of a compact right topological semigroup. So some of you might be familiar with like beta G. So if B is the whole power set algebra, stone B is just beta G. And then that is certainly a situation where all this holds, and we know and love that beta G has compact right topological semigroup structure. In this situation, so does stone B. And then because of that compact semigroup machinery, you can prove all minimal subflows of this thing are isomorphic. We get a canonical universal minimal B definable G flow. All right, and so this is why we care mostly about the externally definable subsets in a group definable in a first order structure, because that's the one that plays nice. So the externally definable sets give us a strongly definable Boolean algebra. Just to revisit those examples, we can actually say exactly what this universal minimal definable float is. It's not too strange of an object. It's a little strange. I'll say a few words about it. It's this so-called doubled circle. And what that means is, let's take our circle. And we, of course, know how the circle and how T and SL2R act on the circle, sort of in the standard way. But I'm going to take the circle and double every single point. So each point is going to double. We're going to have like x minus and x plus for every x that we started with. And the topology, so if I have maybe some other like y minus y plus here, a basic Clopen subset of this space is going to be intervals from a positive version of a point to a negative version of some point clockwise from it. Does that definition make sense?
Clockwise.
Clockwise.
You say clockwise. You want the interval to contain like one of the
yeah. So it's going to contain all this stuff.
Yeah.
That's the interval I want. And so let's just think about the complexity of this space. It is not metrizable. It fails to be second countable. This basis has size continuum. But it's not too bad of a space. It's size continuum. It is what's known as a Rosenthal compactum. I'll revisit Rosenthal compacta a little bit later. So just keep in mind it's a space. It's a bit worse than being metrizable, but it's still kind of nice. That's the flavor I want to convey. All right. Some abstract stuff. So let's grab a minimal subflow of our SGXM. And I want to consider, we're going to really spend a lot of time thinking about the group of automorphisms of this minimal flow. So these are just homeomorphisms of the space that commute with the group action.
Quick question.
Yes.
So I heard double circumference, and then I thought of the Alexandrov double circle, but I think what you're doing instead is taking the split interval and connecting the endpoints.
I think so. I'm not quite familiar with the Alexandrov double circle, but that also sounds very similar to
Yeah, so I
something like
guess
this.
by connecting the 0 and the 1, that helps you make this into
Something
a
that plays with
nice
the
group like
Mm,
stuff,
mm,
which you
mhm.
wouldn't have with the split interval.
Right. Yeah, and we definitely want every point to be doubled, not just like a countable dense set of
Right,
points.
so I'm wondering, as a Rosenthal compact, how does this differ from the split interval?
I think it's actually homeomorphic because like when you take your split interval and you bring the ends together,
No, they're not homeomorphic because the split interval has two isolated points.
S has two min and max are isolated.
So this gets rid of that.
Okay. Thank you.
But it's close. It's
Yeah, there's like you have to glue one little
it's like
thing.
gluing the endpoints of the interval.
Yeah.
All right, so we're gonna look at the group of G-flow automorphisms of these universal minimal definable flows. So just again for this, our running examples, for the circle group, I actually pick up the circle. I can rotate this doubled circle by any angle I want, and that will commute with the circle action. For the SL2R action, that action, I mean, if you think about it, it's like a little too squishy. So you have to be really careful with that. It's going to destroy all but one of the non-trivial automorphisms. The only thing we can do is flip 180 degrees. All right, and so now I can at least state the original form of Newelski's conjecture, modulo a lot of terminology I'm not going to define. So for a group definable in an NIP structure, M, the conjecture asks, is this group exactly this other group? All right, so terminology I've not defined. NIP, this is one of these kind of classical model theoretic dividing lines. It's the negation of the independence property. I will define the sort of dynamical version we're going to need soon. That's tameness from the title. So I will define what tameness is, and then for those of you familiar with NIP, the definition of tameness will look really familiar.
All right, so my conjecture is that this is true if you replace NIP by stable.
Yes. This wacky group GC mod G00. Oh gosh, I'll say a few words about it because I have 90 minutes. So G is a definable group, and I said you can plug in different structures and use the same formulas to get out another group. So instead of taking the model M we started with, take a massive monster model, and then that's this frac C here. So G as defined in the monster, G00 is the largest type definable subgroup of bounded index, or bounded here means kind of in this like monster model sense, like small cardinality. What is relevant to us is that
Let me just. I suspect that the students don't know what the monster model is, so maybe you could just say a few words on that.
oh, it's big saturated, massive saturated model of the theory. Again, so the only thing we're really going to need is that it's a compact Hausdorff group. Whatever this group is, it is a nice compact Hausdorff group. It only depends on the theory of M and the first order definition of G. This conjecture is false. So this SL2R is already a counterexample. And so this is the paper. What was the contribution of this paper? They computed that the universal minimal definable flow was this double circle. And then the automorphism group of that was Z mod 2. In this example, G mod G double zero is trivial. So that's not great. But it is true often. So for so-called definably amenable NIP groups, you do get the conjecture. So in particular, I mean, every stable structure is defined. Every stable group is definably amenable, but this result was known before this work of Chernikov and Simon. But we want to salvage the conjecture for all NIP groups, not just definably amenable. And what we're going to do is we are going to ask, not that we know exactly what this automorphism group is, but that it is some sort of compact Hausdorff group. We need to make that precise because I didn't tell you at all about how to put a topology on this automorphism group. So we need to do that. And we're going to do that with this tau topology. And then just some historical remarks. So it was actually first defined, something equivalent to it was defined by Furstenberg when he was proving his structure theorem for minimal distal flows. Studied further by lots of people. It's been brought into the definable context in work of Krupinski and Pile. So this is a well-known topology you can put on certain automorphism groups in the setting of topological dynamics. And I'm going to spend several slides defining this thing. It's kind of wonky.
Another question.
Yes.
So you say the word salvage appears on the previous slide. So these other results, like the Chernikov-Simon thing, if you prove that this GM is compact Hausdorff with the tau topology, does that imply their results for the?
No, because for instance, Z mod 2 over here for SL2R, that will be that's just a finite group, so that'll be compact Hausdorff in the tau topology. Yeah, so what is
what you're proving is weaker than
the original? Yes.
the original conjecture.
And you cannot get the full original conjecture. So yeah, maybe I should mention what direction is known. So the automorphism group, this G sub M always factors onto G mod G00. So this G sub M is bigger, at least as big as G mod G00, but it could be strictly larger. Right, so towards defining this tau topology thing, we're going to define this for automorphism groups of not all minimal flows, like certain nice minimal flows are going to have this tau topology associated to their automorphism group. So I'm going to spend a bit telling you which minimal flows are going to get this treatment. So given the flow, we can always form its enveloping semigroup. We just take group elements and identify them as functions from X to X in the obvious way. We stick those functions in this huge space, X to the X, massive product space. Take the closure. And you get a semigroup structure just under function composition, because everything there is a function from X to X. And then again, because you have this compact semigroup structure, minimal subflows are isomorphic. And so if I start with a minimal flow, I can view this as building a kind of canonical minimal flow that'll factor onto X. So I'm going to call it this enveloping ideal of X. So take a minimal flow, take its enveloping semigroup, pass to whatever minimal subflow you'd like, because they're all isomorphic, doesn't matter. And in this case, I will say, right, so G sub X now is the automorphism group of M sub X, not of X itself, but of this M sub X. So now, obvious question, which minimal flows are isomorphic to their enveloping ideals? And Auslander actually pioneered this study. He defined the term. Well, he defined the concept. He called it a regular flow. I axed the name regular because that is just an overused word. All right, so this condition on minimal flows ensures that X is isomorphic to your enveloping ideal. So the condition for any pair, I can move X with an automorphism and then obtain a proximal pair. Let me tell you what a proximal pair is. That's going to come up later. So given the G flow, a pair of points in it is proximal. If there is a net of group elements. So that I use the action along this net, and I'm going to squish X and Y together. So you can think of this notion of being a minimal ideal flow as saying, one way of thinking about it is that there are as many automorphisms as possible. So like you will never, for instance, you can never, if X and Y are proximal, I will never be able to move X to Y using an automorphism, because you can argue that X and PX are distal whenever P is an automorphism or even an endomorphism. So this is something like saying there are as many automorphisms as possible. Distal is not proximal. And that might come up later, so I'll really write it. Distal, not proximal. Right, and so then in that case, I will just identify G sub X and the automorphism group of X, because X and this M of X are isomorphic. So enveloping ideals are minimal ideal flows. The universal minimal definable flows are minimal ideal flows. So that's another situation where we make this identification. And I did already on a previous slide. And I can now define the tau topology. This is one way of defining the tau topology. There are many, many different ways of defining this. That's kind of why it's such a mysterious and cool object. There are several different definitions. They interplay with each other in kind of strange ways. Some arguments require like several of the definitions to make headway. Yeah, it's a really mysterious object. There's reason people have been looking at this for a long time. Right, so fix a minimal ideal flow. And I'm going to look at these basic open sets. I'm going to declare these to be basic open in the tau topology. So the set of automorphisms that just move A to have non-empty intersection with B, given some non-empty opens A and B. It is compact T1. It's not Hausdorff. That makes us sad. Because, I mean, we have separate continuity. The moment you have compact Hausdorff separately continuous, we can apply Ellis's joint continuity theorem and then just get an honest-to-goodness compact topological group. We don't have Hausdorff, so we have to settle for compact T1, separately continuous, continuous inversion, and it has this nice property that is useful. Product of two tau closed sets is tau closed. And let me just mention something that'll come up later. We don't need this whole, the basis we wrote down up there is actually way bigger than we need. We only need a subset of that base to be a base. Or I guess for a base of neighborhoods of this P. So I just need to look at neighborhoods A, open A in X, neighborhoods of a single point W, fixed but arbitrary W.
Can I ask a silly question?
Yes.
Why do you spell out tau as opposed to using the Greek letter?
That is a fair question. Because when you are writing a 112-page paper, it is very expensive to use up a character in that way. So
So you want to use tau somewhere else?
yes.
Okay.
Yeah, it shows up. It's just a Greek letter that's nice to have around. You need as many letters of the alphabet as you can. All right, so now we can actually revise our Newelski conjecture in this way. So again, G definable in an NIP structure M. We look at our universal minimal externally definable flow. I want G sub M to be Hausdorff in the tau topology. So that will tell us that it is a nice compact Hausdorff of some sort. It won't tell us what group, but it is a nice compact Hausdorff group. And recently, this preprint by Chernikov, Gannon, and Krupinski proves it in the countable case. So in the case when the model M is countable. So in particular, the group G will be countable because G lives as a set of n tuples in M. So what all goes into this? The NIP assumption is going to tell us dynamical information about these universal definable ambits. So not necessarily about the externally definable one yet, but the action of G on the type space SGM has this dynamical property called tameness, which I will define very soon. And then by magic, i.e. work of Schiller, so by magic, this SGX is also tame. And so then tameness passes to minimal or to subflows, and so then this M is tame. What is the magic? So I mean, Schiller says if you take an NIP structure and just add a whole bunch of predicates for externally definable subsets, and get a new structure M star, then M star is still an NIP structure. It's related to this concept of honest definitions in NIP. All right, so we get this tame flow. So this universal minimal externally definable flow M is tame, whatever that means. Glassner has proven some very intense structure theory for minimal metrizable tame flows, which I will tell you about. And then when G is countable, this flow M is going to be an inverse limit of metrizable ones, and then at every step of that inverse limit, I have access to the structure theory, and we can conclude the theorem. But I'm going to dive into these steps quite a bit. So the first thing is tameness. Let's actually define tameness. So now we're just in the G is just whatever group, doesn't matter. Doesn't have to be a definable group anymore. So just have a G flow. I have some, let's say, non-empty open A0, A1. They're kind of apart, so their closures are still disjoint. And I have a subset of the group. I'm going to say that this pair shatters the subset S if no matter how I partition S into two pieces, S0, S1, I can pick a point in the flow, which, so I think about this point moving around under the group action. It visits various parts of X. And I want it to visit open set AI precisely for those group elements G which are in SI, provided G is in S. If G is not in S, we don't care. But if G is in S, I want it to exactly be in the right AI. A flow is tame if X does not shatter any infinite subset S. So those of you who know what NIP is will immediately recognize the like VC dimension character of this definition. This really is the dynamical analog of NIP. Actually, I am lying a little bit. Nullness is really the dynamical analog of NIP. So because NIP not only says no infinite things are shattered, but there's an absolute bound on the size of finite things that are shattered. But we're going to prove something about tame flows, which is stronger than proving something about null flows. Nice facts about tame flows. Flows under subflows. I should have said subflows, not subshifts. Subflows, factors, products, good closure properties. And now, what's the connection to Rosenthal compactor? I mentioned those a little bit earlier. In the metrizable case, we know a whole lot about tameness. And so for a metrizable flow, the enveloping semigroup, oh, maybe I need to throw the word minimal in front of that too. Sure, let's throw minimal there. We look at the enveloping semigroup, and there's a dichotomy. Either it is really nice, so that's exactly when X is tame. So E of X is going to be a Rosenthal compactum in the tame case, or E of X is going to be huge. We're going to shoot in a copy of beta n. So it's a real dichotomy. So another way to phrase this is E of X has cardinality at most continuum or embeds a copy of beta n. That's an equivalent dichotomy. And then some more references about tameness. Will there be somewhere I can post the slides, like to the website?
Yeah, maybe.
Okay.
Send it to me.
All right. So what did Glassner do? He did this. We're going to spend a lot of time looking at this diagram. I should also mention Glassner did much more than this. Like his diagram has like another whole like row in front, like in between these, or I should say column. So I have extracted a portion of Glassner's structure theorem, which reads as follows. So let X be a minimal metrizable tame G flow. Then there is a diagram as follows. So I start with X. I can build these other minimal flows X star, Z, Y, and these maps between them, satisfying all these nice fancy words. So eta and Y are going to be strongly proximal. Sigma is going to be equicontinuous. Iota is going to be highly proximal. I have a slide of definitions on the next slide. And so just more generally, I'm going to say that a minimal flow X satisfies strong diagram if the conclusion of this theorem holds. So the vocab for strong diagram. Maybe let me actually just draw. That diagram is going to show up a whole lot. Let me just draw it. So what I defined on the previous slide was what I called strong diagram. We will weaken some of the adjectives and get a property diagram. All right, so maps between minimal flows. So I talked about proximality a little bit. So a minimal flow is proximal if every pair is proximal. A map between minimal flows is proximal if every pair in the same fiber is proximal. Strongly and highly proximal are strengthenings of proximal. I won't get into those too much. We will mostly just need proximal. Equicontinuous is kind of the opposite of proximal. So that says, so I mean, a flow is equicontinuous if as each group element is a continuous map from this compact X to itself, and I want that to be an equicontinuous family of continuous maps. And then the map is equicontinuous if this kind of happens fiber-wise. All right, so mostly we'll interact with proximal. So what did Chernikov, Gannon, and Krupinski do? Their argument essentially showed that if a minimal flow X satisfies strong diagram, then GX is Hausdorff. And their proof does not need all the properties. So their proof really only needs this weaker property diagram where everything that is more than just proximal is weakened to only say proximal. So here, and let me, in fact, modify this. I will only indicate what diagram is, and I'll tell you just all of these things. So Y is a proximal minimal flow. This is equicontinuous. This is proximal, and this is proximal. And everything inside is minimal. That's diagram. Yeah. And everything inside is minimal. So it turns out that diagram characterizes Hausdorffness of G of X. So given a minimal flow, I form, so how did I get to G of X? I formed the enveloping ideal of X. I looked at the automorphism group of the enveloping ideal. I equipped that with the tau topology. That is Hausdorff exactly when that happens. I just want to mention it is really not that much of a stretch, the proof, given the existing literature. I mean, so like if you read reference to here's Ostlander's minimal flows book, a close reading of that, this theorem falls out pretty quickly. All right, so now we are really coming to the part where it's a set theory talk now. So most of the model theory is behind us. So what we're going to do, we're going to prove the revised Newelski conjecture with no cardinality constraints using forcing and absoluteness, in particular Levy absoluteness. So let me tell you a little bit about the Levy hierarchy. So we're looking at formulas in the language of set theory. Delta zeros are ZFC equivalent to ones where all the quantifiers are bounded. That's like an example of a bounded quantifier. There is X in Y such that something quantifier free happens. Sigma ones, we're allowed to put an unbounded existential in front of a delta zero. Pi ones were allowed to put an unbounded universal in front of a delta zero. Delta one means just both sigma one and pi. And I'll just point out that really this ZFC equivalent to is doing a lot of heavy lifting here. I mean, a formula on its own cannot be both pi one and sigma one non-trivially. So this is really saying some property there is a way of expressing it that is sigma one. There is a possibly very different way of expressing it that looks better. I will mention sort of the prototypical delta one formula. Saying a set is finite is delta one. It is not delta zero. And delta one formulas are really nice. They are absolute between transitive models of set theory. We are going to apply this mostly between V and a forcing extension. Actually, entirely between V and a forcing extension. And even better, and the forcing is always going to be a collapse. So we're going to apply Levy absoluteness between V and then extension after you collapsed some cardinal to be countable. All right, so let's start thinking about delta zero, delta one formulas that are going to show up in topological dynamics. So saying that a set B is a base for a Hausdorff topology on a set X, that is going to be delta zero. Notice if I tried to say tau is a topology on X, that would be no good. When you start running through what a topology is and you get to that step of like unbounded, like arbitrary unions of open sets should be open, that's going to be impossible to express in a delta zero fashion. So we have to focus on a base. But upon so doing, it's fine. Similarly, for uniform structures, I can talk about being a base for a Hausdorff uniform structure. I can, given a topological space presented in this fashion, I can think about a group acting on it and say that the group is acting by homeomorphisms. That's all fine.
What is 19?
19 is a wonderful paper by Jendra Zapladal, his interpreter for topologists paper. So he has a lot more to say about like moving topological spaces between models of set theory.
Really? So what's the actual title?
Of his paper?
Yeah.
It's like something like interpreter for topologists. So yeah, we're using like a very, very simple fragment of some of the ideas found there. So for topological spaces, this is fine, but if we want to start talking about compact spaces, it becomes harder because the statement B is a base for a compact Hausdorff topology on X is pi 1. And there's no way around that. It is properly pi 1. For every open cover, we can find a finite subcover. That is a universal, unbounded universal quantifier. So we need a workaround. So we're just not going to compactify. So we're going to do as follows. So a preflow is going to be an action of our group on a precompact uniform space by uniform isomorphisms. And then given such a thing, I can complete the precompact uniform space. I will get a G flow that I'm going to denote X hat. I will call a preflow minimal if X hat is minimal. This, so working with preflows is going to be annoying. It's going to be kind of finicky, but the payoff is a drop in complexity.
What is precompact?
It means that the completion is compact. Formally, it means that for every entourage, I can cover the uniform space by finitely many balls of determined by that entourage. So talking about being a minimal preflow, ends up being delta 1. So that's really nice. That's our drop in complexity. There's a little bit of a lemma to get minimal in there too. It's not too bad. But yeah, the main work here is that we're talking about pre-compact uniform spaces instead of compact topological spaces. That's the real key here. And so now we can state the main theorem much more precisely. Given a minimal preflow, these formulas are both delta 1. So these are formulas in the parameter x talking about properties of x hat, but I just want to emphasize that it's a formula about x. So these formulas saying that x hat is tame and that g sub x hat is Hausdorff are both delta 1. As a corollary, we get the revised Newelski conjecture. For any minimal tame flow, G sub x is Hausdorff. And I'll prove it. So we start in our universe V, collapse some cardinals, go to this forcing extension W, making x second countable. I mean, make anything countable if you want. Make your group countable if you want. But let's do that. So now the key thing is, so we started with a flow in V. Moving to W, x is no longer a flow. We lost compactness because compactness is pi 1. X is a minimal preflow up in W. So working in W, let's take the preflow x and complete it. It is then a minimal metrizable tame flow because x hat tame is delta 1. Glassner's theorem in W tells us that x hat satisfies strong diagram. G of x hat is Hausdorff in W. And then because that is a delta 1 statement, we go back down to B. So you'll notice we didn't need the full strength of the theorem. We needed tameness. We needed x hat tame to be sigma 1 to move up. We needed gx hat Hausdorff to be pi 1 to move down. So those are the directions we needed to get this to work. All right, so the rest of the talk is just outlining this argument a little bit. Are there any questions at this juncture? All right, so some remarks on the proof. The tameness bit is not too bad. What we're going to do is we're going to consider some like basic open A0, A1. Again, I should mention when we say things like this.
Before you get on.
Yeah.
Wait the prescribed 15 seconds before cutting off the questions. Earlier, you threw in separate continuity, and I was confused because separate continuity usually the only way I've seen it is you have a product and you're separately continuous using factors, but here you just had one space and you're talking about separately continuous.
Oh, so I mean, when it's saying that the group is separately continuous, I mean, we have the map from G cross G. So I can hold the right argument and move the left argument. I can hold the left argument, move the right argument.
Yeah,
This is in the group.
G,
Yeah.
I understand.
And then something I really ought to emphasize, I was talking about like these statements were talking about bases for a topology, bases for a uniform structure. And so when I talk about preflows on pre-compact uniform spaces, I really have a distinguished, the way I present that object, I have a distinguished basis in mind that comes along for the ride. And so I just want to emphasize that one more time, that when we talk about open sets, we're going to really try to only range over things from this distinguished basis so that we don't have to do an unbounded search.
Whenever you're doing forcing and topology, you need to roll the base because that doesn't change.
Right,
to the
exactly.
extension, but topology, sure. That's actually my thesis.
Right, so tameness, grab some basic open non-empty sets. Let's insist that they are uniformly apart. This will ensure that when passing the X hat, when I take their closures, they're disjoint. And we're going to build a tree of attempts at finding an infinite subset of our group shattered by A0, A1. So put like G0, G1, ... Gn into this tree if A0, A1 can shatter this finite subset, G0 through Gn. And then it's not too hard to show X hat is tame exactly if for every A0, A1, again, coming from this basis, so that is not an unbounded for every, that's a bounded for every, we're asking for a tree to be well-founded. Well-foundedness of trees is a classical delta 1 concept. GX hat being Hausdorff, we're going to break it apart into two directions. So we need a sigma 1 definition for it, and we need a pi 1 definition for it. The sigma 1 definition is not hard given what we have seen, because we have seen the characterization that given a flow X, GX is Hausdorff if and only if diagram holds. Let's think about the statement diagram. Diagram says there exists a whole bunch of stuff and maps between them nice properties. So that's kind of promising. That sounds like putting a big exists quantifier in front of some less complicated stuff. And this more or less does work. The only wrinkle, though, is you have to talk about pre-flows. The statement diagram is really about flows, and so you have to kind of take all the components of diagram and rephrase everything so that makes sense for pre-flows and ensure that you're writing down things that are delta 0 or delta 1. So here is an example of that kind of reasoning. So given the minimal pre-flow, we can write down a statement about the pre-flow, ensuring that X hat becomes proximal. And then it ends up being this statement here. So for every U in our base for the uniform structure, there's a V in that base for uniform structure. So for all XY in X, not X hat, we don't have access to X hat. We only have access to X. So for all XY in X, there's some group element such that if I fatten up X and Y using V, then translate by G, I get into a U small set. And it's little arguments like this, but for all of those properties showing up in the statement diagram. Like you need like equicontinuity is a bit of a pain to express, but it can be done. Things like that. All right, and then we need a pi 1 definition for GX as Hausdorff. And this is probably the hardest one.
This one is the one used to.
Yeah, and this is the one we needed. Yeah, this is the one we needed, and it's the painful one. So why is it hard? At some point, we have to interact with the definition of what this G sub X is. It is the automorphism group, remember, not of X, or X hat in this case, but of the enveloping ideal. And so here's a quick way of phrasing the key difficulty. So if I have some minimal preflows, I should have removed the hats off X and Y. So X and Y are preflows. Then we can think about the statement, is Y hat isomorphic to the enveloping ideal of X? That's really complicated. That is not at all delta 1. So generally what's going to happen, like imagine, so I have a minimal flow in V, and I compute its enveloping ideal in V. I move both of those minimal flows to some forcing extension W, and then complete them. And then I try to compute in W the minimal ideal, the enveloping ideal of X. It could be strictly bigger than what I computed back in V. So that's really the key difficulty. So we need to dive in a little bit to the construction of M of X. So let X just be a minimal flow for a second. There is some set. I is bounded here by the cardinality of x, if you want. Such that I can form the product x to the I as just a big product G flow under the diagonal action. And M sub x lives as some minimal subflow of x to the I. And mx is actually the largest such minimal flow I can make in this fashion. So it is universal among minimal flows which appear in powers of x. All right, and so this sort of motivates what we're going to do is we're going to try to show that the failure of gx being Hausdorff. It's easier to build things than to not build things. So I'm going to show that the negation is sigma 1. So yeah, like what is the witness? How are we going to witness the failure of Hausdorffness? So we're gonna say it's equivalent to the existence of some set and some preflow subset of x hat to the I with certain nice properties. That's the goal. And let's revisit that fact about this nice small basis around an automorphism P for the tau topology. Right, where I guess in this fact, x is a minimal ideal flow, so that g sub x is odd x. So staring at what it means for this fact to, well, what does it mean to have a net of automorphisms converge to both the identity and something else in a topology with a basis given by this? Well, it would mean something like this definition. So this is exactly what this definition extracts. So a minimal preflow. No demands that x hat be like an enveloping ideal or anything like that. Just any minimal preflow, this definition makes sense. We'll say that it has wild automorphisms if there is existential quantifier. There is some net of automorphisms, some non-identity automorphism P, such that for any A and B from our distinguished basis, and for all large enough I, PIA intersect B is non-empty, PIA intersect PB is also non-empty. So this is sort of what it would mean in a case where the tau topology is defined to have a net converging to both identity and P. But we can write down this definition even in situations where the tau topology doesn't quite work. This statement is sigma 1. Yeah, because nothing about this. Yeah, there is a net. That's the only existential. Everything else is bounded. And then this is the pi 1 characterization. So gx hat is not Hausdorff, provided there are some set and some minimal preflow which lives in this product x hat to the I with wild automorphisms. And now let me just talk a little bit about this. This might look a bit suspicious. How do we bound the complexity of this given that x hat is here? Saying that y is a subset of such things is actually not bad, because to be a member of x hat just says, I mean, I am some Cauchy net of points of x. Saying that I live in this product just means that I look like an I tuple. What gets hard is saying, for instance, to say that y would be equal to x hat to the I would be a much more complicated statement. That would be pi 1 almost surely. But just to say that the members of y have this form, that's simple. That's going to be delta 0. All right, and then just some questions that are suggested by all of this. As a corollary, which maybe I should have actually bolded as a nice corollary. Because we've just shown that minimal tame flows have GX Hausdorff, and because we have a precise structure result for when GX is Hausdorff, we have a partial generalization of Glassner's structure theorem to the non-metrizable context. So minimal tame flows all satisfy diagram. What about strong diagram? The minimal metrizable tame flows all satisfy strong diagram. I would love for that to be true generally. I really expect it to be true. I imagine one could do it by like really understanding Glassner's work very carefully. It's a very intricate and difficult paper. But I think it's doable. The other thing that's kind of lacking from this work, especially like the since we have the revised Newelski conjecture instead of the original told us exactly what this automorphism group was, and it was invariant of the theory. It didn't depend on which model the theory we plugged in to get our group. So I'll ask just for universal minimal externally definable flows. Do their automorphism groups only depend on the theory in the first order definition? And then this is more of a vague point, but all of the absoluteness machinery was just a really small instance of Levy absoluteness. We were always taking collapses and forcing extensions. I would love applications in dynamics that use more interesting forcings, perhaps. That's subjective.
Particular, there are stronger absoluteness results.
Of course.
Sigma 2 and so forth, if you assume large cardinals and look at wooden stuff and so forth.
All right, so then I just have references and I'll stop there.